Welcome back to the NMR Challenges series. In the previous video, I provided this NMR challenge for you. And today, we are going to explain the solution step by step. If you have already solved it, then you can match your answer by the end of this video. So let's start today's NMR challenge.
I'm really happy that we have reached to our 10th NMR challenge, and this NMR challenge is also very interesting, and I'm really sure that you are going to enjoy the solution of this problem. So while determining the structure of this organic compound, we are going to follow all those steps which we learned in the last videos. So first we will calculate the index of hydrogen deficiency, then we will look 1H NMR, and after that we will look 13C APT NMR. Before solving this problem, we are going to revise all those steps which we are learning since beginning, and we will revise chemical shift value for 1H NMR and 13C carbon NMR as well. This is very important to keep revising because this practice will make you perfect. And here are those steps. So first step is calculating the index of hydrogen deficiency, which is also known as degree of unsaturation, and this is the formula. So this formula is 2 multiplied by number of carbon atoms plus 2 plus number of nitrogen atoms minus number of hydrogen atoms minus number of halogen atoms divided by 2. So the value gives number of pi bonds or rings, or it could be both. If this value is equal to 5 or greater than 5, then we can blindly say that it has one benzene ring, and this benzene ring will correspond to the 4 value because it has 3 pi bonds plus 1 ring. Then we will see 1H NMR, and as we said that number of signals is equal to the how many types of protons are there. Splitting patterns will give us information about the number of neighboring protons or substitution pattern on the benzene ring. So here is the splitting pattern formula, n plus 1, where n is equal to the number of adjacent protons which are equivalent. And for determining the substitution pattern on the benzene ring, we should also know the J coupling value. So we will learn when we will have those kind of problem. And 1H NMR chemical shift values is also very important to understand shielding and de-shielding of the protons. As I told you, primary carbons, hydrogens coming in the shielded region from 1 ppm to 1.2 ppm. Secondary carbon hydrogens are slightly de-shielded as compared to the primary, and tertiary hydrogens are slightly more de-shielded from 1.4 ppm to 1.9 ppm. And we also learned that when methyl is attached to the ketone, then it comes from 2 ppm to 2.6 ppm, and it is quite similar value for methyl attached to the benzene ring such as in toluene. So it is also coming in the same region. Acetylene protons is slightly de-shielded as compared to the methyl attached to the aromatic rings. It comes from 2.5 to 3 ppm. This is very interesting value. When oxygen attached to the carbon, then hydrogens are coming around 3.5 to 4.5 ppm more often, and it could be higher also, but usually you will see in this range. And when it is attached to the nitrogen, then it can come from 3 to 4 ppm. We also learned that hydroxy and amines protons are acidic, therefore they can undergo exchange from one molecule to another molecule, therefore their values are not fixed, and it is coming from 1 to 5 ppm. The aromatic protons comes from 6 ppm to 8.5 ppm, sometimes overlap with the alkene protons. This depends on the nature of the alkenes. Aldehyde protons comes from 9.5 ppm to 10.5 ppm, but carboxylic protons always comes after 10 ppm to 13 ppm, and it is slightly broader signal. So we should remember these values because it is very important to determine the structure of the compounds. Then the third step is 13C APT NMR. So we will look 13C APT NMR, and we know that this NMR gives all kind of carbon signal, but in 13C depth NMR, we don't see signal for quaternary carbon, the carbon which doesn't have any hydrogen. It also tells us how many types of carbons are present in a molecule. And we also learned that methane and methyl peaks are 180 degree opposite to quaternary carbon and methylene carbon. So in this spectra which we are going to show here, the quaternary carbon and CH2 signals coming in the upward direction, or we can say in a positive phase, and methane and methyl carbon are coming in the negative phase. But remember that when you are solving in MNOVA or any other software, then you can change it. You can change this phase by yourself, and then it could be opposite. But here the NMR which we are looking, in that case we are following this pattern because those NMRs are presented in this way. It is also important to remember some of the chemical shift values for carbon. So here are some chemical shift value for the carbon. When it is primary, So it is coming up to 35 ppm. When it is secondary, it is slightly deshielded. Tertiary is coming maximum 55 ppm. When it is connected to the oxygen, then it comes from 50 to 70 ppm more often, but it could go to 90 ppm depending upon the structure. Acetylene carbon comes from 70 to 90 ppm, and benzene carbons comes from 110 to 170. These values for the functional groups is very important to remember. Ester comes from 165 to 175 ppm, but amides could be slightly lower than ester. It can be from 160 to 175 ppm. Carboxylic acid is slightly higher from 175 to 185 ppm. Aldehyde always coming in highly deshielded region from 190 to 200. Therefore, it is easy to distinguish between carbonyl carbon from ester or carboxylic acids. Now we are ready to take this challenge. First, we are going to calculate the index of hydrogen deficiency using the formula 2 multiplied by C plus 2 plus number of nitrogen minus number of hydrogen minus number of halogen divided by 2. 2 multiplied by 9 plus 2 plus 0, 10 hydrogen. There is no halogen, divided by 2. So 10 divided by 2 is equal to 5 degree of unsaturation. When the degree of unsaturation is more than 5, we can clearly say that 4 degree of unsaturation belongs to benzene ring and 1 degree of unsaturation is left. You can further confirm the presence of benzene ring by looking the 1H NMR. You can see that there is a signal in the aromatic region. So this compound has one benzene ring. Now we are going to interpret 1H NMR. In 1H NMR, there are 5 signals. One is this, 2, 3, 4, 5. So it has 5 types of hydrogen. Now this signal 1, it is around, let's say, around 1.3 ppm, and it is correspond to 3 hydrogen. It is triplet. This triplet indicates that the number of neighboring hydrogen would be 2, and this is belongs to methyl group. So number of neighboring hydrogen 2, it means CH3 attached to CH2 group. So this is the possibility that this compound have CH2, CH3. Let's look at the signal number 2, which is around 2.5 ppm, and this corresponds to 2 hydrogen. It is quadrate, right? You can see the zoom part. This quadrate indicates that the number of neighboring hydrogen is 3, and this belongs to CH2. So we can clearly say that this compound have CH2, CH3 group. Now we are 100% sure that this compound has ethyl group. Now look at the aromatic part of this 1H NMR. If you see the signal 3, 4, 5. 3 correspond to 2 hydrogen, 4 correspond to 1 hydrogen, and then 5th is 2 hydrogen. This pattern indicates that this benzene ring is monosubstituted. So benzene ring is monosubstituted. Okay, so now we are missing 1 degree of unsaturation, right? Now look at the carbon NMR. In the carbon NMR, we have signal in the around 173 ppm, and this signal correspond to ester group, ester carbon, right? And the upward signal, we know that belongs to the carbon having no hydrogen or CH2. So this one 27 is belongs to CH2, and the downward signal belongs to CH3 or CH, right? So this is the deshielded part. So for sure this is belongs to this CH of the benzene ring, and this one is belongs to methyl group, right? Because it is in the upfield region. Now one signal is left at 150. What do you think? So this signal is quaternary carbon, right? So probably this is the signal belongs to this carbon. Okay, this 150. And now you can clearly say that this is the signal C type, this one, and this one is B type because both are equivalent, and this one is A type. So that's why you are seeing here 3 signal. So now what information we have? We have following information that benzene ring is monosubstituted, okay, and this compound has ester group. So ester group means that uh, this R, this R part could be, this R part is CH2, CH3, but there is a possibility that ester could be like this also, like this, right, in which oxygen is attached to the benzene ring. Now we have two possibility. Let me draw both the possibility. First is that oxygen is attached to benzene ring, then ketone, then CH2, CH3. And second possibility is that the benzene ring is directly attached to keto group, then oxygen, then CH2, CH3. Here, chemical shift knowledge is very important. If this is the structure, then this CH2 should come in between 3.5 to 4.5 ppm. But if you look in the given problem, it is coming around 2.5 ppm, right? So this quadrant is coming around 2.5 ppm. So, and in this structure, the CH2 should come around 2.0 to 2.5 ppm. So we can clearly say that correct structure for the given problem is this one, not this one, just because of the difference in the ppm of the CH2 signal. Otherwise, you cannot differentiate between the ester signal. Ester will be most probably will be close to each other, and this carbon is attached to the oxygen. That's why it is going around 150 ppm. But if it is the case, then it will not go to 150 ppm, right? But this is the most important signal. This is the most important characteristic signal. I hope that you really like this problem. Next problem I am going to take from the Pavia spectroscopy book, because one of the students want to see problems from the Pavia spectroscopy book. So this is the NMR spectroscopy problem from the Pavia book. The page number is 217 and the problem number is 204. So in this problem, we you can see that we have normal carbon NMR, depth 135, depth 90, and 1H NMR. And we have to determine the structure of this compound. So in the next video, we are going to learn about depth 135, depth 90 NMR, and how to interpret this problem. So don't forget to subscribe my channel. We will see you in the next video. Thank you very much. Take care. Bye bye.